Good morning. Today we look at linear differential equations. So this is the second last section in this chapter on differential equations. Okay, now our linear differential equations, they look like this. You have dy dx plus p times y is equal to q. So here p is a function of x only, and then q is also a function of x only. Okay, so you have this is a function of x only, that is a function of x only. So if you have a differential equation that you can rewrite in this form, then the differential equation is what we call linear. Now something we should note that all linear differential equations are exact or can be made to be exact. So that means if the way the question is given, our linear differential equation is already exact, then you can solve it as an exact differential equation. If it is not, then you know how to change it so that it becomes an exact differential equation. But the way that we solve these linear differential equations is quite simple, very easy. I think one of the easiest of all the types that we have. So we look at examples of how we work these out. So number one, we have x dy dx plus 2y. This is equal to x to the power of 2. So this, as the question is given, it is not exactly in this form because we have a coefficient of dy dx over here. So first thing we need to do is divide everything by x. So dividing everything by x, we will have dy dx. This is 2 over x times y. This is plus. And this is equal to x. So x squared divided by 2 is x. And now this is in the form of a linear differential equation. So we can see that this 2 over x is a function of x only, and this x is a function of x only. So we say that our p is equal to 2 over x. Now the way we solve these linear differential equations is by multiplying throughout by an integration factor. So when we were talking about exact differential equations or making a differential equation exact, we did talk about an integration factor. And we said that our integration factor, we called it r. We got this by saying e to the power of p dx. So here, this is how we will get our integration factor and then multiply throughout by that integration factor. So we have r is equal to e to the power of the integral. P is 2 over x dx. This is e to the power of 2 ln of x, which is x squared. So now that I have an integration factor, I'll multiply the entire differential equation by that factor. And then I have x squared dy dx plus 2x times y is equal to x to the power of 3. Now, if we look at the left-hand side and you look at the terms that you have, here I have x squared, and then over here I have 2x. If I differentiate x squared, I get 2x. Over here I have dy dx, and on this side I have y. So if I differentiate y, I get dy dx. So this looks like it's in the form v u prime plus v prime u. And as we know, this is the product rule. So I could always write it as vu prime like this, because I have a function multiplied by derivative, the derivative of this function multiplied by the first function as it is. So we can see that when I multiplied by the integration factor, I created on the left-hand side the product rule. So making use of the product rule, I can now rewrite the left-hand side as x squared times y prime. This is equal to x to the power of 3. Because again, when I differentiate this using the product rule, I would have this one as it is, multiplied by the derivative of y, which is this part here, plus the derivative of x squared multiplied by y as it is, which is that. So when you multiply by your integration factor on the left-hand side, you should be able to condense it as the product rule. Okay, then from here I have a derivative is equal to some function of x. To get rid of the derivative, all I do is integrate on both sides. So I have the integral of x squared y prime dx. This is equal to the integral of x cubed dx. And the integral and the derivative will cancel out. So I have x squared times y. This is equal to x to the power of 4 over 4 plus my constant c. And then from there, we can simplify to make it look a little bit better. And we have 4x squared y minus x to the power of 4 is equal to c. So remember, when I multiply everything by c, multiplying this constant by 4 doesn't change the constant in any way, in that it doesn't change from being a constant to then being a function of x. So 4 times c, we just leave it as c. It is still some constant. And that is basically how we work out our linear differential equations. And number 2. We have dy dx minus 1 over x y. This is equal to ln of x. So this one here is already in the form that we like. So we just identify our p, which is negative 1 over x. And then we work out our integration factor. R is equal to e to the power of the integral of minus 1 over x dx. And this is e to the power of minus ln of x, which is minus 1 over x. So I have my integration factor. I'm going to multiply everything by that integration factor. And what I have is minus 1 over x dy dx plus 1 over x squared y. This is equal to minus ln of x over x. Okay, so here, just looking at this, here I have minus 1 over x. The derivative of minus 1 over x is positive 1 over x squared. Here I have y. The derivative of y is dy dx. So I can condense this as the product rule. This is negative y over x prime. This is minus ln of x over x. And then to get rid of the derivative, we integrate both sides. So minus y over x, this is the integral of minus ln of x over x dx. Okay, the negative can go out, and over here we can see that we have we can use substitution because the derivative of ln of x is 1 over x. So here we have u du. Yeah, we have u du, and that is just u squared divided by 2, and our u in this case is ln of x. So integrating with minus y over x, this is ln of x to the power of 2 divided by 2, then we add our constant. Okay, then you can multiply out your denominators, so that will leave us, sorry, there's a negative here that I took out, so there should still be a negative here. And then we multiply by 2x, or negative 2x, so this will give me 2y is equal to x ln of x squared plus cx. Okay, so again, when I multiplied this constant by 2 or negative 2, it didn't change from being a constant, so still a constant there. And then this x here is the one that I multiplied throughout like that. X squared plus 2y dx is equal to dy. So first we must write it in the standard form. So we have dy dx minus 2y. This is equal to x squared. Okay, so now it is in standard form. So our p is negative 2. And our integration factor r is e to the power of negative 2 dx. So we integrate negative 2 dx. This gives us e to the power of negative 2x. And then we are going to multiply this with our differential equation. So we have e to the power of minus 2x dy dx minus 2e to the power of minus 2x times y, and this is equal to e, or x squared, e to the power of minus 2x. Okay, so again, we look on the left hand side. here we have e to the power of minus 2x. The derivative of e to the power of minus 2x is negative 2e to the power of 2x. Then we have y there. The derivative of y is dy dx. So we can condense this as y times e to the power of minus 2 e to the power of x prime. This is x squared e to the power of minus 2x. So here we have the derivative. To get rid of the derivative, we integrate on both sides, and then we will end up with y e to the power of minus 2x. This is the integral of x squared e to the power of minus 2x dx. And then this is an integral we've done before where we use by parts. So we pick what we will differentiate and what we will integrate. So we've done this before. We must pick x squared to differentiate because eventually the derivative will go to 0. So we have x squared, 2x, 2, and then 0. And then here we have e to the power of minus 2x. When we integrate that, we have negative a half e to the power of minus 2x. And then when we integrate that, we have 1 over 4 e to the power of minus 2x. And then when we integrate that, we have negative 1 over 8 e to the power of minus 2x. So this is positive, negative, positive, negative. Then we draw our arrows like that. So y e to the power of minus 2x, this is equal to, the first one is positive x squared times negative a half e to the power of x. So that will be negative a half x squared e to the power of minus 2x. And the next one is negative 2x times 1 over 4 e to the power of x. So that is negative a half x e to the power of minus 2x. Then the next one is a positive 2 times negative 1 over 8 times that, which is negative 1 over 4 e to the power of minus 2x, and then we can add our constant. The last one will be the integral of 0, which is a constant. Okay, so now we have this, and that is our solution. Y times e to the power of minus 2x minus a half x squared e to the power of minus 2x minus a half x e to the power of minus 2x minus 1 over 4 e to the power of x plus a constant. Again, you can rewrite this to make it look nicer. Maybe multiply everything by 4. Also, we see that e to the power of minus 2x is common, so you can also divide throughout by that. Just remember that your constant will have this, so we can write it like this. 4y is equal to negative, or even do this, 4y plus 2x squared, then we've divided by e to the power of minus 2x, then plus 2x plus 1, which we will add, well, there's no constant to add that to, and then this is equal to c e to the power of 2x. like that. Okay, so that is one way you can rewrite it. Okay, and then look at some of the questions from exercise 5.8.
Hawe fuck off man. Makanda kwene. Kanto kisanga no kweli wangu ndadi bano kuziu. What time was this? And it's in India. What's that man? I'm not going to do that. I'm not going to talk to you.
Good morning.
Good morning, that imagine.
Okay, let's start with number 1. We have dy dx plus 2yx is equal to x. Okay, so this is already in standard form. So from here we can see that our p is equal to 2x. Now we just need the integration factor. So r is equal to e to the power of 2x dx. And this is e to the power of x squared. Okay, then multiply everything by e to the power of x squared. We get e to the power of x squared dy dx plus 2x e to the power of x squared times y is equal to x e to the power of x squared. Okay, so again on the left hand side we check that this is the product rule. We have e to the power of x squared. The derivative of e to the power of x squared is e to the power of x squared. Then we multiply that by the derivative of x squared, which is 2x. And then we have y and the derivative of y. So we can condense this as y e to the power of x squared prime. This is x e to the power of x squared. Then we integrate on both sides, so we have y e to the power of x squared is the integral of x e to the power of x squared dx. Okay, so here we're only missing a 2 in order for this to be the derivative of our numerator. Then we can rewrite this as e to the power of u. So we can put a 2 here and a 2 outside, and a half outside rather. So we have y e to the power of x squared. This is a half 2x e to the power of x squared dx. So y e to the power of x squared. This is a half times e to the power of x squared plus our constant of integration. Okay, so you can, as always, multiply by the fraction that we have, but I think this looks just as good. 3. Let me just see how it's written in the book. Okay, so it's written dy dx plus y tan x is equal to sec x, but we can always write that as y prime plus y tan x is equal to sec x. Okay, so now that I have that, it is in the form that we like. Dy dx is alone. I have y multiplied by a function of x, and then on the other side I have a function of x. So my p here is tan of x, and then my integration factor, this is e to the power of the integral of tan of x dx. So we know that when we're integrating tan of x, that's the same thing as sine over cos, and from there, let me just, this is e. Okay, so the numerator would be the derivative of the denominator if we had a negative here. So I add a negative here and a negative outside. And now this is e to the power of minus ln of cos x. And this is e to the power of ln of sec x, which is sec x. Okay, so then I will multiply my differential equation by sec x. So I have y prime times sec x plus y sec x tan x. This is equal to sec squared of x. Then look on the left hand side, sec x, the derivative of sec x is sec x tan x, and then y, the derivative of y is y prime. So using the product rule, we can say that y sec x prime, this is equal to sec squared x. And then to get rid of the prime, we integrate on both sides. So we say y sec x is equal to the integral of sec squared x. So we have y sec x. The integral of sec squared x is tan x plus our constant of integration. For number 5, we have di dt plus I is equal to sine t. And with this one, we are given some initial conditions. We are told that I of 0 is equal to 0. So that means we will have to work out what the integration constant, the constant of integration is. Okay, but we still work it out in the same way we did. So it's already in the form that we want. We just need to work out our integration factor. So P here is equal to 1. Okay, so that's the only function of t that we have here. So our integration factor will be e, the integral of 1 dt. So this is e to the power of t. Then this e to the power of t, we multiply it throughout. We have e to the power of t di dt plus e to the power of t times I is equal to e to the power of t sine of t. Okay, then I have e to the power of t, the derivative is e to the power of t. I have I, the derivative of I is di dt. So this is I multiplied by e to the power of t prime, which is e to the power of t sine t. And then to get rid of the prime here, we integrate on both sides. So we have I times e to the power of t is the integral of e to the power of t sine t dt. And to integrate this, we use by parts. So di. Now, because here it doesn't really matter which one you're differentiating or integrating, they are pretty much the same. So I'm going to integrate sine t and differentiate sine t, integrate e to the power of t. So here I will have cos t. The integral of cos t is minus sine t, and this is just e to the power of t, e to the power of t. Okay, so you can see that the pattern will just continue, and I stop here because sine t e to the power of t is exactly what I have over here, except this one will be negative, and then when I can take it to the other side to give me 2, and then I divide by 2. Okay, so here we should take note that the integral of e to the power of t times sine t dt, this is plus, minus, and then the last one is plus, and our arrows. So we'll have e to the power of t sine t. Then the second one is minus e to the power of t cos t. And then the next one is minus e to the power of t sine t, minus the integral of e to the power of t sine t dt. And then this we can take to the other side. We will have 2 e to the power of t sine t dt. This is e to the power of t sine t minus e to the power of t cos t. Then divide everything by 2. We have the integral of e to the power of t sine t dt. This is a half e to the power of t sine t minus a half e to the power of t cos t, and then plus our constant of integration. So this is equal to I times e to the power of t. So we have I times e to the power of t. This is equal to a half e to the power of t sine t minus a half e to the power of t cos t, and then we add our constant of integration. Then just remember that we were given initial conditions, so we're looking for a particular solution. So now we substitute t is 0 and the value of I is going to be 0 as well. So what we will have is 0 here, because I is 0. This is 1. This is equal to 1/2 times e to the power of 0 times sine of 0, which is 0, and minus 1/2 e to the power of 0 cos of 0 plus c. So this is 0. This is minus 1/2. Sorry, cos of 0. Yeah, cos of 0 is 1/2. Cos of 0 is 1. So here I am getting C is equal to 1/2. And C is equal to 1/2. Okay, so now that I know what C is, I'm going to T. This is 1/2 e to the power of T sine T minus 1/2 e to the power of T cos T plus 1/2. Okay, then we can multiply everything by 2 so that the half cancels, and also divide everything by e to the power of t. So see, there's e to the power of t, e to the power of t, and so on. But I think that is also fine. Number 7, we have cot x dy is equal to 1 minus 2y dx. So first thing is to rewrite it in the standard form. So we have dy dx. This is equal to 1 minus 2y divided by cot x, or multiplied by tan x. And then we collect y and its coefficient on the other side. So this means that dy dx, this is plus 2 tan x times y is equal to tan x. Okay, so that is now in standard form. Then we can see that this is our P. So P is equal to 2 tan x, and our integration factor is e to tan x dx. So we've already integrated this before. We got ln of sec x. So our r is 2 ln of sec x, which is ln of sec squared x, which is sec squared x. Just a moment. Okay, so this is just, sorry, the way I wrote this is not correct. This is e to ln of sec x, then it becomes sec squared of x. Okay, so now we multiply throughout. We get sec squared x times dy dx plus 2 sec squared x tan x times y. This is equal to sec squared x tan x. Okay, then on the left hand side you see we have sec squared of x. The derivative of sec squared of x is this, and we have y. The derivative of y is that, so we can condense that to give y sec squared x prime. This is sec squared x tan x. Okay, and then now we just need to integrate to get rid of this derivative. So we have y sec squared x is equal to the integral of sec squared x tan x dx. Okay, so here we have tan x. The derivative of tan x is sec squared x. So this is just tan squared x divided by 2. Yeah, because this is u du. So we have y sec squared x is equal to tan squared x divided by 2, and then add our constant of integration. Then, as always, you can play around with it, rewrite it so that it looks a little bit better. Then one more, get number 9. Number 9, we have r dq dt plus q over c is equal to v, and we are told that g of 0 is equal to 0. Okay, so this is not in standard form. We need to divide by capital R on both sides. So we have dq dt plus 1 over rc times q. This is equal to v over r. So remember, the only variables here are q and t. This r is a constant, this is a constant, that is a constant, that is a constant. Our p is this, so our integration factor, so here I don't want to say r because of this r here. Integration factor is e to the power of the integral of 1 over rc dt. And this is e to the power of t over rc. And then we multiply as we always do. So this is e to the power of t over rc dq dt plus e to the power of t over rc times q, which is v e to the power of t over rc divided by r. And then we look on the left hand side. I have e to the power of t over rc. The derivative is t over e to the power of t over rc, and then we multiply by the derivative of this, which is 1 over rc. Q, the derivative of q is dq dt, and then we can condense that. So we have q e to the power of t over rc prime. This is equal to what we have on the right hand side, v e t to the power of rc divided by r. Okay, then to get rid of the prime, integrate on both sides. So we have q e to the power of t over rc. This is equal to v and r can go outside the integral. Then e to the power of t over rc dt. So q e to the power of t over rc. This is v over r. Then the integral of this is this, the way that it is. So e to the power of t over rc. And then we divide by the integral of this, which is 1 over rc, which is the same as multiplying by rc. And then here we have a constant. So this constant, I call it k because it's different from this one. This c was there in the question that we are given. So call your constant by another letter. Okay, then see that these two will cancel and simplify as far as possible. So we have q e to the power of t over rc. This is equal to vc e to the power of t over rc, then plus our constant k. Then remember we were given some initial conditions. Here I wrote g, but I meant q. Okay, so now we just substitute. Q is 0 and t is 0. So on the left hand side we will have 0. And then here we will have VC, and this is 0. So e to the power of 0 is just 1. So VC plus k, which means k is equal to negative VC. And then I rewrite this equation with negative VC. Okay, so my solution, my particular solution is this. And minus VC. And that is it. So the other questions in the exercise, you would do them pretty much the same way. Like I always say, very important that you practice, because that is the key actually. You don't practice, you will not be able to do any of these in the test. So make sure that we practice. And then tomorrow we will finish off this chapter on differential equations by looking at Bernoulli's equations. The Bernoulli's equation, these are very similar to linear differential equations. In fact, it's just a little manipulation, and then you can rewrite a Bernoulli's equation in term as a linear differential equation, and then we solve it in the same way. Okay.